Well, hello and welcome YouTube, Mr. Robinson back here with yet another math video for you. I'm going to get straight into it here. I actually have had a couple days of, they haven't been my best here, so I'm just going to go right through and, do what I can here. These two videos will come in succession with each other. This one is focused on tangent lines. Specifically, how tangent lines work with their associated central angle, what we're going to be doing with the lengths of those tangent lines, and how we can work them quadratically. Almost sometimes I think they like to represent some of these this way. Any circled problems that you see are ones that I'm going to do. So the ones that they start with actually do start with the lengths. After that, they go to angles. But the next video after this will deal with secant lines and their lengths with secant lines. I don't even know if we go into degrees with those ones. And also a secant line with a tangent line and what we can do there. I don't know the number of problems off the top of my head. I'd say somewhere around 10, 11, 12 or so. But like I said, I'll get to it. Part of this is assuming you've seen quadratic things with me before. So I'm not doing a big bit on reteaching those other than doing problems of that variety. The main thing that comes into play in these, as anything else, is once you kind of hear about a topic, I'll get to go through them faster, but of course every problem has its own unique strategy, all depending. I haven't done them before, except for maybe helping some of my students out, but it's nice to hear that strategy out loud with me as I see it for the first time. And of course, there may be more than one way to do a problem. I'll see if I will. Okay, let's get this thing started here on this number 8 for the tangent line business. In the figure, QS equals 5, RT equals 12, the length of RT, and RT is also a tangent to the radius QR with the point of tangency at R. Find the length of QT. All right, so the big thing that you'd want to, here it goes. The big thing you want to know about tangent lines is that they intersect with radii at 90-degree angles. And I'm sure I've mentioned this before. I'm sure it's been brought up, especially when we've talked about diameter in tangent lines and inscribed angle measures being 90. But yes, this is a 90-degree angle measure. Now, another instance of this is when you see this length of QS as 5, this is a radius of your circle because Q is your center. QR, therefore, is also a radius of your circle, which means this is 5 as well. So we are trying to find the length of QT right here. And what you can see is what's represented as a right triangle, with 5 and 12 being the leg lengths, and then QT being the hypotenuse. So you have some options on what you can do here. Option number 1, which what most people probably should go for here, is working out Pythagorean theorem. 5 squared plus 12 squared equals QT squared, and then finding that QT. Option number 2 is option number 1. It is understanding your right triangle here and actually knowing, and I'm going to skip the steps right here. If you want to work this out, go ahead. But if you do this correctly, where you square these, add them up, and take the square root, you get QT equals 13. Now, my option number 2 that I'm stating is this is a 5, 12, 13 Pythagorean triple. And if you know some of your right triangles, then you would actually just know that answer straight up. So it's still part of Pythagorean theorem, but it's just the knowledge of a 5, 12, 13 special right triangle. Pythagorean triple, I should say. Option 3 would be a little bit more, and this is me going into a heavier introduction on quadratics. Let's say that you didn't recognize that QT should be figured out straight up, and maybe you wanted to find this length. Well, this entire thing is some 5 plus x or x plus 5, where you work out Pythagorean theorem again, right here, but you got to square x plus 5 and solve for x. Now, the difference here is you really got to work this quadratic in a way where you might have to factor. 5 squared plus 12 squared is 25 plus 144. Well, I guess this is me working out that other version. And x plus 5 quantity squared is actually x squared plus 10x plus 25. You are squaring the binomial. It's not just x squared plus 25. You got to also double the product of these two. If you FOIL it and expand it out, you'll see what I mean. Now, this is 169 on this side. And if you want to solve for a quadratic here, your best bet, outside of some... Actually, you know what? There were other versions of what I could have done here. I'll give you an option 4, but I think it brings you straight to here. But in quadratic form, if we set everything equal to 0, then you can work out the factorization of this. So this factors into some sort of x and x thing. Again, I'm not going to get deep into the understanding of the factoring part. This is more the geometry and then using the algebra within. But this factors into x plus 18 times x minus 8 equals 0. And zero product property would show you that x either equals negative 18 or x equals 8. Again, if you've done the algebra stuff with me, then you know what this is. And these would be answers to help you get to the length of QT. The thing is, though, if x is a negative value, you can't have negative length. You can't have zero length. This one is what's known as an extraneous solution. This one does not apply. Algebraically, it does. Geometrically, physically, in our world, it does not. The 8 does apply, though. So if x was 8, if this thing did work out here, then you get 5 plus 8, which is still 13. You can see why the first/second option are the better way to go for this thing, just finding QT in general. But if you had to find this individual x, well, if you had to find the individual x, I would still probably find QT and subtract 5 from it, because here you had to work a greater deal of solving and factoring. But I'm showing you this because we got to do this for a couple of the next problems here, because they're represented as quadratics right off the bat. All right, numbers 9 and 10 here. The segments in each figure are tangent to the circle at the points shown. Find each length. So AB is tangent to circle D, and AC is tangent to circle D. Tangent means touching it just at a single point, even though the drawing isn't probably best represented for that. But it touches at B and kisses right off of it and keeps going. Unlike a secant line, which goes through and hits twice. Now, the thing about tangent lines, without going deep into any sort of proof here, is that all tangent lines, in this situation, meeting at a single point, they're congruent to each other. This is congruent to that, and that's the straight up setup that we need for this one. 2x squared equals 8x. Now we're going to solve for x and use that to find the actual lengths themselves. I should do the same thing here as I was doing in the other problem. I should set it equal to 0 and then factor. So if I subtract 8x from both sides, I get 2x squared minus 8x equals 8 equals 0. And find a common factor such as 2x. This creates yet another product for us. This allows us to solve using the zero product property. Either I have 2x times x minus 4 equals 0. Either 2x equals 0 or x minus 4 equals 0. If 2x equals 0, divide both sides by 2, then x equals 0. If x minus 4 equals 0, add 4, x equals 4. Now, if you substitute 0 into here, you get the same issue as you got with negative 18 before. You get a non-positive length, which doesn't physically really apply for us. That doesn't work out. If you substitute 4, it works out just fine. And you can test both of these as well. 2 times 4 squared is 2 times 16, which is 32. And if we did this correctly as far as solving, 8 times 4 should also be 32, which it is. So both of these are 32 here. They said find each length. Each of these should be 32. That's the value of x that makes it true. No other x value would make these equal to each other unless they both became 0, which is not really one that we can have. Number 10 is going to be the same thing here as this number 9. We have two tangent lines here, and so this should be congruent to that. That means the values here, y and y squared plus 7, or over 7, excuse me, are equal to each other. So we need to find out which value of y makes this whole thing true. And they're not asking you to guess and check. You know, go ahead and use the algebra. There may be more than one answer here that can apply. Maybe not in this case, though. If I multiply both sides by 7, then that rids my fraction issue here. And I'm left with 7y equals y squared. I'd rather subtract the 7y over to keep my y squared positive, set it equal to 0. And I have y as a common factor here, which is once again a goal, creating this zero product property setup, which we can then use to solve for. So either y equals 0 right here, or y minus 7 equals 0, therefore y equals 7, one or the other there. Y equals 0 is one of those ones, again, that will be an extraneous solution. I substitute 0, I get 0 here, 0 squared over 7, which is 0. They're still equal value, but those aren't lengths. So y equals 7 should work here. If I substitute that, obviously 7 for y makes this one 7. 7 squared over 7 is 49 over 7, which is 7. It looks like the values of these guys, SR and RT, are both 7 in length, as these were 32 here. If that's the y value that we need, 7. Okay, moving forward. Now these ones after this I don't believe associate the lengths, but the next video that I do will associate lengths again, and they might only do that. And I think we're going to run into a couple quadratics there, so be ready for some of those again. Okay, so the next thing that we're doing here is we're going to be talking about degrees again, and we've done a bunch of these before, and this one, I mean, has a different little scenario to it. Let's let's look at what's happening. PR is tangent to circle Q, and PS is tangent to circle Q right here, and find the measure of angle Q. So let's do this in a practical approach, starting off with the concept of these should be right angles right here. Both of these. They're both right angles right there because it's a radius intersecting with the tangent line at that point of tangency. Now, if you look at this entire structure here, this makes a quadrilateral, four-sided shape. And its interior angle sum is actually 360 degrees, that if you add 42 with the two 90s and then the measure of angle Q, which we don't know, that gets us 360 degrees. Now the part that I want to bring about really is right here. I know I can combine all three like terms. Let's just combine those two for a brief moment. I'm even actually going to move the 42 over. So 180 plus measure of angle Q plus 42 equals 360. Okay, I put those two together because I want to subtract those for us here. Let's subtract 180 from both sides. And then what you're going to see here is the measure of angle Q plus 42 equals 180. And I bring about this because this will always happen when you have two tangent lines intersecting at the same point outside the circle. I'm sorry, I didn't mention what this was called. Your circumscribed angle right here, it's called a circumscribed angle because it's an angle that circumscribes your circle, touches it at one point. Your circumscribed angle and its associated central angle will be supplementary to each other. We know central angles are equal to their intercepted arc value. Great. But what we haven't used yet is this being supplementary to this. We've used them in inscribed circles, such as 1, 2, 3, 4. Opposite angles were supplementary, boom, boom. But now this time, this angle, circumscribed, and its associated central angle are supplementary. So any other time we see that, that's what I'm going to work off of. I get to skip the 90s right here, boom, boom, and go straight to here. Boom plus boom is 180. And by the way, the 90 plus 90 was also 180 as well. Anyway, subtract 42 from both sides. I am going to get the measure of angle Q is 138 degrees right there. That's how large that guy is. Looks like we're going to do the same thing here. They say find the measure of angle P, and it looks like we might have to solve for X first to make that so. Now, this is the same scenario, though. These are 90-degree angles. Boom, boom. This circumscribed angle and associated central angle should also add to 180 degrees. So 4x is 180 degrees. Divide both sides by 4, you get x equals 45. Measure of angle P is x degrees, so measure of angle P is indeed 45 degrees. No real other way that I'd be going about that problem than what's there. All right, here we go. We have another set of tangent ones right here that does make those 90 degrees if that matters for what we got to do in the problem. And this is 56 degrees right here. First, we got to find the measure of angle AOB. Well, if you really ignore all this, you see this other thing. It's a circumscribed angle and its associated central angle right here. That means that this plus the 56 should be adding to 180, just as we saw before. If you subtract 56 from both sides, then the measure of angle AOB is 124 degrees. So this is 124 right there. And I write it in because we might have to use it. They asked for another part of this problem, and there's more stuff to do. All right, measure of angle OGF. OGF. We're looking for this guy right here. Okay. I see a couple different ways we can do this. It depends on what you want to go about and do. For one, you know what? Maybe I will. Okay. For one is this. These are radii in your circle. That means these two are congruent to each other. That means this is an isosceles triangle right here, which means its base angles are also congruent to each other. This OGF is also congruent to OFG. And we know if this is 124, then this is also 124 inside here. Basically what we have is an isosceles triangle, and these two unknowns are the same. That's one way we can solve this thing. I can do some sort of 124 plus 2x is 180. The two angles in your triangle, isosceles, are 180. Subtract 124, well, it should give you 56 again. Actually, it makes me wonder how I can bring up that 56 in its own way. 56 there, divide by 2, you get 28, which is the measure of angle OGF then. Measure of angle OGF equals 28 degrees. That's one version of it. I don't know if that's what they wanted. That's one version of it, using a vertical angle bit. I'm wondering if there's a way that they want to talk about with the circumscribed angle there. Maybe not necessarily, but alternatives really are. We have a diameter right here as well, which means we have semicircle business, and I bring that. Oh yeah, that's totally how we should do this problem. All right, so another version of this is 180 degrees right here. This is a semicircle right there. Now, when you look at OGF, OGF is also AGF. And AGF is an inscribed angle with this intercepted arc measure right there. This AF right here, I'll just put an X right there. If we find that X, we take half of it, and we can get that here. But the whole semicircle is 180 degrees. Now we know, well, I guess we're going to get the same answer if we do this. The whole thing's 180 degrees, but we know that this part, gosh, I bring in parts and I got to take them out now. We know that this part should be that same 124. We talked about this before. Here's a central angle that's 124 degrees. That means its intercepted arc right here is 124 degrees. Well, this unknown AF, I'll put an X right there. This unknown AF, those two should add to 180 because that's a semicircle right there, right? Subtract, you get that 56. Now that is the intercepted arc for your inscribed angle AGF, which is the same angle as OGF right here, and the inscribed angle is half the measure of its intercepted arc. So measure of angle OGF or AGF, not OGA, it's half the measure of its intercepted arc, so half of 56, which is 28. I'm seeing a bunch of different ways to go about that. It's all about how you want to navigate your shape. But if you didn't really see the isosceles triangle thing, I want to work something we've seen before. I don't know. I'd say those are the two good ones to go with for now. All right, I'm going to move forward. All right, number 16. Which statements correctly relate angle BDC and BAC? Select all that apply. We know that they're supplementary, right? So here we go. Are they complementary? No. Are they supplementary? Yes. Are they congruent? Not necessarily. There's no reason to assume that. They don't look at either. Are they right angles? No. DBA and DCA are right angles, but not these ones. The sum of their measures is 180. Yes, that's what supplementary means. It's impossible to determine a relationship. No, it's not impossible. We know that B and E, they're supplementary. They add to 180. Straight up. Now, again, the congruent, these if this said DBA and DCA, B, C, and D and E, B, C, D, and E would have been the answers for that. All right, hey, let's skip critical thinking because that wasn't the problem that I gave them. All right, KJ. Now this time it's an actual literal tangent ray right here, but just this portion right there is where we get not only congruent with that if we had to, but 90-degree angles would go here because the central, the radius at the center. All right, KJ tangent circle C and KL tangent circle C. Measure of arc ML is 138 degrees. Find the measure of angle M. All right, M is an inscribed angle right here. They really should have said JML, but M is an inscribed angle right there with this intercepted arc right here. Okay, the intercepted arc is equal to this central angle right here. The inscribed angle is half the intercepted arc. So what we want to do is we want to find the measure of this central angle. That'll become this intercepted arc measure. We'll take half of that. We'll get measure of angle M. So first we find the measure of angle JCL. As we add that with 40 degrees, remember here's a circumscribed angle, here's the associated central angle. They should be supplementary. They add to 180. So the measure of angle JCL, if you subtract 40 from both sides, equals 140 degrees. So this is 140. Now, the central angle, therefore, is also 140. The measure of arc JL is equal to the measure of angle JCL. That's also 140 degrees. So now this is 140. Now we talk about, so that's this whole guy. Now we talk about the measure of angle M, which is half of that because it's an inscribed angle. Not a circumscribed angle, but an inscribed angle. It's half 140, which is 70 degrees right there. So that is measure angle M. Again, JML is probably the better term for, but that's 70. And that information is probably useful for measure of arc MJ. Oh, well, the 140 is important for that. Measure of arc MJ is just the last part that gets us 360 degrees right here with 138 and 140. So the measure of arc MJ plus 138 plus 140 equals 360. Combine like terms, or combine these two, you get 278. Subtract 278 from both sides, we get that answer. 82 degrees there. Yeah, that's the last part. I think I have one more. Yeah, okay, explain the error. In the given figure, QP and QR are tangents. A student was asked to find the measure of angle PSR. It's where that X is labeled. Critique the student's work, correct any errors. Since PQR is a circumscribed angle, that's correct. PQR and PCR are supplementary. PQR, PC, that's also correct. The central angle and that one right there, they're supplementary. They had 180. So measure of angle PCR is 110. Let's see if that works. Yeah, this is 70. So measure of angle, I'm going to write this just to have you guys know why that is. Measure of angle PCR plus the 70, the PQR is 180. They're supplementary. Subtract 70, measure of angle PCR is 110. Okay, so this is 110 degrees. Since PSR is congruent to PC, well, that's not true. Since angle PSR is congruent to angle PCR, PSR is also 110. No, there's no reason to assume that this angle is congruent to that one. The intercepted arc is congruent to that, this 110 right here, but not necessarily the angle right here. You got to find the angle in a different way. In fact, so let me point that out. Where's the figure? This one right here. Look at this angle A versus what I could draw right here. Let's call it like that one right there. They're kind of giving you this angle. Right here that just touches, on the circle right there. And they're saying, hey, this is congruent to this. No, that's not always true. No. They made it look so, and maybe it's close to it, but it's a bad reason. Maybe it's 111 degrees. I don't know. But let's correct what's there. So this is the part that's wrong. There's no reason to assume that those are true. Tell me the theorem or something that we've talked about that would prove that. What you can do is you can basically hunt for this intercepted arc right here, because that angle we're talking about, that PSR, is the inscribed angle for this intercepted arc here. So you have two options to find it. One is that the 110 that you have is has an intercepted arc right here that's 110. That's not this angle, that's this arc right here. And 360 minus 110 would give you this 250 right here. So this whole thing here is 250 degrees, which I should be probably writing in blue. That's 250 degrees here. Now the inscribed angle is half that measure. So measure of angle PSR is half of 250, which is 125 degrees. So yeah, not quite 110, a little bit more than that. Yeah, no reason to assume that is. So that's probably the way that I'd be going about it there, at least as far as what we're talking about. Okay, and that is it for the tangent bits here. Now I am making another video in immediate succession to this one regarding secant lines, tangent line, secant line things. So just hold tight for that one. That will deal with probably more on the quadratics and lengths. I don't think angles are really associated with them. I think we've already done the tangent secant things with angles. Yeah, so we've already done those. So that'll do it for this one, guys. We're going to go into the tangent secant ones. I'll see you in a hot minute. Take care. Have a good one.